So there you are. You're trying to approximate a chi-square distribution. You need to estimate the probability that a certain variable, which has a chi-square with some n degrees of freedom, is between two specified values. And you're wondering to yourself, my n, it's kind of big. It's like 20, let's say, I'd like to just use a normal distribution, but you're starting to feel a little guilty about it. And you're wondering what you can do to alleviate that sense of guilt. Let's take a look. So there you are. You're trying to find a couple of values, a and b, such that your variable x is between a and b with a 95% certainty. And x, let's say, is a chi-square variable with n degrees of freedom. And just to be nice, let's just pick an n. Let's just say n is 20, just for example. Okay. And so you know that if you think about the chi-square 20 variable, that this is vaguely close to, a normal distribution with what has some mean. Mu is actually n minus 1, which in our case is 19, and the variance is twice n minus 1, which is 38. And so you could replace this by such a normal variable and come up with these estimates a and b. But now, if you think about it actually, chi-square with 20 degrees of freedom, how normal is that? Let's take a look. We have on the one hand the chi distribution here, which has been normalized so that its mean and mean is here at 0 and its standard deviation is at 1. Here is 2 degrees of freedom. I'll do 1 degree of freedom. Even you see that it's it's pretty not normal, but you make n big a little bit. Here we are over at 3. It's still pretty darn skew. Here we are at 6. Still pretty far off. 9. You can see that it's getting closer. 12 over at 20 where we were before for our example looks like this. And this is still not so great, in terms of how close it is to normal. If we go up to 30, oh, that's all the way over to 80. But yeah, like even here at 50, you can see that it's, kind of visibly, a bit off from the standard normal variable, going way out to, whoops, let's go to like 100 or so, 150. Yeah, so in any case, you can see over here it's, over at 150, it's getting pretty darn close. But, if you're at these high values and you're trying to really understand what's going on at these tails, because you really need to know that you're at the 99.99th percentile instead of only the 99th percentile, it gets a little dodgy to use these approximations. You start to really want to use some variables other than chi-squared or derived from chi-squared, which are a better fit for the normal distribution. If x is a chi-squared 20 random variable, then by definition, square root of x is a chi 20 variable. Now the point is that that the square root of x is a whole lot more normally distributed than x is. If we knew the mean of square root of x and the variance of square root of x, then from that we'd be able to get a very nice confidence interval as desired for a normal random variable. So let's suppose, knowing that this is very normal, we would then quickly be able to get, some numbers c and d, such that root x is between these two things. But then that tells you that, so the probability that this would be, let's say, 95%. And you can find these c and d just because you have a normal variable, and if you know the mean and variance, then we just, you can translate that to a standard variable, look it up on a chart. We'll do that in a moment. But, okay, so if you get that, then you would know that the probability that x is between c squared and d squared is also 95%. That would be great. So the question is, how do you find c and d? Well, all we need to know is these things, and then, we're home free. So let me, just for the moment, call this thing just mu and this thing sigma squared, and you can see that if root x is normal, then it's approximately, then let's call this some variable y, and if you looked at y minus, I don't know, I really had to change letters. The square root of x is a perfectly good thing to say. If you take the square root of x, you subtract off its mean, mean root x, and divide out by its variance, or excuse me, by its standard deviation, then you'll get a normal variable z, right? And so, well, we know that, for example, 95% of the time, the variable z is going to be between -2 and 2, for example. And that's going to be the probability that -2 less than root x minus the mean of root 2 over the standard deviation of root 2, root x, sorry, root 2, that's supposed to be an x, excuse me, is less than 2. And that is the probability that, so I'll just multiply that around, -2 standard deviations of root x is less than root x minus mean of root x is less than twice the standard deviation of root x. Okay, this is all 95%. That's the probability that -2 standard deviations of root x plus the mean of root x is less than root x. I'm not really doing anything very deep here, but I'm just going to writing this out. Is less than 2 standard deviations of root x plus the mean of root x. What do I need to know? I need to know then what is this mean of root x and what's the standard deviation of root x. And how do you figure that out? Well, root x is a chi variable, and so we just have to know what is the mean and the standard deviation of the chi variable. And that's kind of the rub. Well, it's not like we don't know it, but it's a little bit of a pain. And so what do we find? Well, if root x is a chi variable with n degrees of freedom, so that just means it's the square root of a chi-square variable, then the mean is given by this beautiful formula, root 2, gamma of n plus 1 over 2 divided by gamma of n over 2. And the standard deviation is the square root of the number of degrees of freedom minus the square of the mean. Well, and of course this gamma is our loved gamma function. So, gamma is the gamma function. And the gamma function is this beautiful, somewhat mysterious function interpolating the factorials. It is a well-loved function, but we love it not particularly because it's super easy to just take a number and plug it in. We love it because it's, it has other beautiful magical properties. Alright, so for us, we are interested in the case where n is equal to 20. Just for the original problem we were interested in up here. We wanted to get a 95% confidence interval for a gamma squared 20 variable. Okay. And for n equals 20, this expression that we're looking at is is gamma of 21 over 2 divided by gamma of 20 over 2, or 10. And let's ask the oracle. So we say, Wolfram, what is gamma of 21 over 2 divided by gamma of 20 over 2? And it says, well, it is this nice expression, which is approximately 3.12. 3.12. All right. And so we find that the mean of our chi variable with 6 degrees of freedom is root 2 times 3.12, which is about 4.42. Great. So the mean is 4.42. The standard deviation is the square root of n, which is 20, minus 4.42 squared. All right, so square root of 20 minus 4.42 squared, and we see 0.68. All right, and there we go. So what do we find? If I just grab this over here, this was our 95% confidence interval. So 95% is that probability. So with 95% certainty, we know that our chi variable is between minus 2 times 0.68 plus 4.42, and 2 times 0.68 plus 4.42. And that is, what is that? 0.68, 1/3, 1.36. That's 4.42. So that is 3.06. 3.06 is less than root x, is less than 1.365.78. Okay. So root x is between these things, and therefore there's a 95% probability that our chi-square variable, which we're interested in, is between the square of that and the square of that. Now, that's an answer, but how does it compare to other possible answers? We did a bit of work there, and you know, we had to struggle a little bit with that gamma function. We really had to ask for some help from Wolfram there. How necessary was that? Let's just compare it to the much easier way of just using the central limit theorem straight up. So if we know that our chi-square variable x with 20 degrees of freedom, so this is chi-square 20 variable, is approximately normal, and the mean, as we've seen, is 19, and the variance is 38, twice the mean. Then we know that if we look at x, we subtract off the mean and divide by the standard deviation, then this is approximately our normal variable. And then we say that the 95% chance that the probability that our normal variable is between 2 and minus 2. And then we got that that x minus 19 over root 38 between 2 and minus 2. And then that gives us, well, let's see, so 19 minus 2 root 38 is less than x is less than 19 plus 2 roots of 38. Okay, and that's our 95% confidence interval that we get in this way. Okay, what is this actually? Square root 38 twice the square root of 38. So this is 19 minus 12.3, less than x, less than 19 plus 12.3. And so we get a 95% confidence interval of, that's like 6.7, that's less than x, is less than 31.3, is that? Yeah, 31.3. And geez, that was so much faster. Oh my gosh. Why did we do that other thing? Wait, how do these confidence intervals compare? Here we got 6.7 and 31 before we got 9.3 and 33. So we shifted this thing over 3 units to the right, and we shifted this thing over just a touch to the right. Gosh, which answer is right? Well, of course, confidence intervals are not unique. But let's just go ahead and take a look and see how these probabilities actually shape up. Like, what we're really doing is we have x as our chi-square variable, which is normal-ish. And somewhere over here is 6.7. Somewhere over here is 31.3. This is it's supposed to be the x value of 31.3. And we're saying that we're getting 95% of the mass here in the middle. And so we can check that by just computing. Let's just actually compute. If you have a chi-square 20 variable, how much is less than 6.7 and how much is more than 31.3? Okay, and so here we see it. If you have 20 degrees of freedom and we look at 6.7, then you can see here on this chart that there's just a tiny little sliver of area to the left of that. It accounts for 0.2%. 0.2%. Now, if 95% is supposed to be in the middle and we're doing things nice and evenly, then we want actually 2.5% on each side. Okay. To the right of 31.3, it's actually 0.051. Okay, so in fact, this is a reasonable confidence interval. It seems pretty close to 95%, but it's pretty skew in that it's kind of shifted over a bit to the left. On the other hand, if we look at this confidence interval that we got originally, all right, so for 9.36, we find that our left tail looks like that, and accounts for little over 2% of the distribution. So in this one, if we have a picture of our distribution, which is very ugly, but let's just pretend this is 9.36, and here is going to be that value is going to be 33.4. Then in this case, we get about 2% over here. All right, and we see that on the right for this distribution, we have another reasonable little chunk there. We get on our right tail about 3%, which again accounts for a total of 5%, but you see it's much more evenly distributed. Now, when we did this, we actually got a little bit lucky. When we did that second approximation, if you think about what really went into it, when we make these bounds on our normal distribution by saying that there's a 95% chance that our standard normal variable is between -2 and 2, what's really going into that is we're imagining that there's only a roughly 2.5% chance that it's less than -2 and a 2.5% chance that it's greater than 2. Now, it turns out that both of those estimates were incorrect when we applied the central limit theorem to our chi-square variable. One of those things, instead of being 2.5%, ended up being close to 0, and the other, instead of being 2.5, ended up being close to 5. The fact that these things ended up balancing made us get a bit lucky, and we ended up with a 5% confidence interval, but this was a little bit of luck, right? It came from being wrong twice in two different ways. So you can see that that it was a more robust calculation using the chi variable instead. Of course, there was some technical hurdles to doing that with the gamma function. Now, in all honesty, there was nothing super special about using the chi distribution. I mean, what did we really need? What did we really need? We needed some variable which was closely related to our chi-square distribution, but which was much closer to normal and which we could compute more easily. So it turns out that the square root of a chi-square variable does that. The disadvantage was that the mean and variance were kind of a pain to write down, but it turns out we could have used the square root of twice the chi-square variable. The square root of twice the chi-square variable actually has a much easier mean and variance to write down. We could have used the cube root of the chi-square variable divided by n. That also turns out to have an easy to write down mean and variance. And so there are just a number of kind of transformations you can do to a chi-square variable which make it a lot more normal as n gets not nearly as large as it would be otherwise. And a lot of these other things turn out to be very useful for writing our interval estimates for our confidence intervals. Let's do one more example just for fun. So another one of these nice transformations is the following. So if x is chi-square with n degrees of freedom, then if I take the square root of 2x, and n is reasonably large, then this is close to normal, closer than the chi-squared itself would have been. And it has a mean of the square root of 2n minus 1, and a variance of 1. Okay, so this makes it a lot simpler to think about. So like if we wanted then to look at n equals 20 and get a 95% confidence interval, again we'll say 95% is the probability that the standard normal variable is between -2 and 2. And now if we look at the square root of 2x, we subtract off its mean and divide by the square root of its variance, which is 1, so we're not really doing anything, then this thing is going to be pretty close to normal. And so this over here is the probability that -2 is less than, let's see, so root 2x minus the square root of 39. This is the probability that -2 is less than root 2x is less than 6.2. Let's call it 6.2. So this is the probability that 4.2 is less than root 2x is less than 8.2. Okay, and let's go ahead and square those things. 17.6, let's say, is less than root, no, I just squared it, is less than 2x, is less than 8.2 squared is 67.2. Okay, and now I'll divide out, and so we got, what do we got, like 8.8 is less than x is less than 33.6. Okay, and let's go ahead and compare that to what we had before. So when we did our chi distribution, which took quite a lot of work, we got these intervals 9.36 and 33.4. Here we're getting there we go. Here we're getting 8.8 and 33.6. Okay, that's like pretty close. But there's a number of these approximations, and some of them aren't too bad, but just using kind of a blind central limit theorem can be a little bit tricky because the chi-square distributions just want to be so not normal.